Uh, well, so this seminar we'll speak in English because our speaker is not yet comfortable in French. Although he is a student from Paris, he was a student at Paris 7. As I was saying, this seminar is a little bit like a family, and this an example is Rahman, who is, well, how should I put this? Do you come like a bit my nephew, because he was a student of Boban Veličković, and Boban Veličković, Andreas Vilaveches, and me, we were all students of the same person, Ken Koonen at the University of Wisconsin in Madison. So in that sense, we are a little bit like a family. And it's my great pleasure to have met Rahman here in Paris and to have followed his path from the very beginning of his research to now that he has become a postdoctoral researcher at the Technological University in Vienna. we also have some projects together, and I'm very disappointed that his original plan of coming to Paris to visit us did not work out because of some COVID test, which turned out, unfortunately, to be positive. He had the best intentions to come and be here in person. So Rahman comes originally from Iran. We have had the chance, Chris, Andreas, and me, to visit the institute, this wonderful Institute of Mathematics in Tehran, where many of our colleagues come from. And they have excellent students. And in spite of the pressures that the political life makes in the life of mathematics and mathematicians, the colleagues in Iran have managed to keep a very, very high level of research in mathematics and mathematical logic and well, set theory, like Rahman, who is now shares his life between Iran and Europe. He's now one of our colleagues in Europe. So Rahman's specialty are forcing axioms, and he's going to tell us about forcing axioms, tears and smiles. So to you, Rahman.
Okay, thanks for introduction, Mirna, and let me also thank the other organizers, at least I know Francois. So this talk is prepared for, for the general audience, and so I will be a bit imprecise in the beginning. So I'm not a senior lecturer, you know, and so maybe my talk is not like Andres' talks that, it's rich with philosophy and other things. So, but I try to give you the motivations and provide mathematical intuitions for definitions. There will be some technicalities, but you can just ignore them. Okay, here we go. What we want to talk first is about the consistency and independence in mathematics, or in general in logic. So a theory is a set of axioms. So we have a language. It consists of some symbols, and we can form well-defined sequences that play the role of words and sentences and so on. And a theory is just a list of sentences. And we say that this theory is consistent if it cannot prove everything, or it cannot prove the contradiction. A proof is like we consider the axioms in T as premises, and then with the rules of inference, we find conclusions. So the conclusions have proofs from that theory. So it's a general definition, right? The reason I don't want to be precise is that we may not need to work with the usual logics. There could be other logics like modal logics and etc. And the definitions are a bit different, but still you can talk about these concepts and ask similar questions. When we have a theory and we have a sentence in the same language, we say that this sentence is consistent with that theory if when we add it to the theory, then the theory remains consistent, meaning that the theory cannot provide a proof for the negation of the sentence. And a sentence is said to be independent from a theory. Again, the sentence is in the same language of the theory if S and its negation both are consistent with the theory. So there is neither a proof for S from T and nor a proof for the negation of the sentence. You can stop me and ask questions, by the way. I mean, I don't want to finish the slides, so I could be a bit slow. So there are two questions when we have a theory. We can ask when the theory is complete or when the theory is incomplete. Incomplete means that there are independent statements. If a theory is complete, then either it proves given a sentence, either it proves it or it proves its negation. And if it is not complete, is there a complete extension, consistent, of course, consistent complete extension of that theory? Okay, the first question, if we have answers for that, right? For example, Gödel's incompleteness theorem says that under some conditions about T and the language, T is not complete. We will see examples. But the other one is easier to answer. It's a theorem of Lindenbaum that every first order consistent theory in a countable language has a complete extension. So in some sense, a complete extension is good, right? It's like a picture given by Platonism in mathematics, but unfortunately by Gödel's theorem, mathematics is not complete, at least if we assume ZFC is the, we consider ZFC as the foundation of mathematics. But so that's good to find a complete extension, but complete consistent extension, but we cannot work with that. For example, in general, not always, but if, for example, we expand ZFC and find a consistent complete extension, then it is not subject to Gödel's incompleteness theorem. That means probably we cannot even work with that because somehow it is just something we know that it exists, but we don't know what is inside. So the idea, I mean, the proof is by axiom of choice. I mean, we can use it, but the general idea is like this tree. It's not a proof. Okay, this is like we start from T and we make a tree, but at each stage we add a node if it is consistent. Okay, if it is not consistent, so here we assume in this picture this is consistent, this is consistent, all of them are consistent. If it is not consistent, we don't put it there, and then that branch is dead end. We continue with the other branch. So in some sense, we can, in a countable language, we can enumerate the sentences and add it to the theory. So now, if you pick a cofinal branch through this tree, then it gives you a consistent, complete extension of the theory. So it could be anything. Maybe there is a statement phi, which is independent. Maybe you pick a branch which contains phi, another branch contains the negation of phi. So in some sense, such a complete extension is not very useful, but it has this very trivial property that if your complete extension proves a statement, then the original theory cannot prove the negation, of course. But this is not what we are interested in. We are interested in the opposite direction, which is false. But okay, we can still be interested in false things. So here is mathematics from this point of view. The language of mathematics, at least 99% of mathematics can be formalized within this language, which consists of only a binary relation, which is membership, and the logic is the first order logic, and the theory is ZFC, is bunch of it's not finite, but a bunch of things which are really intuitive. Like we take the union if two sets are equal, if and only if they have the same elements. We have choice functions and so on. We have power set, meaning that if we have a set, we have another set which exactly consists of the subsets of the original set. And by Gödel's incompleteness theorem, ZFC is incomplete. So this theorem, probably you know that in some sense it was ignored by mathematicians because they thought that this kind of witnesses for the incompleteness of ZFC are not useful in mathematics. They are artificial and they are not subject to practical mathematics. Later, other people, I think, like Paris, and Harrington, maybe, they discovered statements in the terms of like Ramsey theoretic statements, which of course are equivalent to the essence of Gödel's incompleteness theorem. But we know that later, of course, there is the method of forcing, and we will talk about that. Okay, now the problem or the question is that we have this incompleteness. We cannot be truly Platonist, but okay. So can we have sort of completeness inside this, or can we find some reasonable extensions which look like complete theories? So this is not a well-defined thing. I just use it for giving the idea. So so you can assume that T is ZFC or any extension or something related to CFC. So we have this, we have a theory, consistent theory, and we have a method. We can show that some statements are independent of T or they are consistent with T. Okay. So we are interested in a pseudo completion of T with respect to M, meaning that if we have a method, or let's see the next one. Okay, we write like this. I don't know how to read it. Sorry, I invented the notation, but I don't know how to read. This means that we can show that the theory T does not provide a proof for the negation of phi using the method M in addition to the usual probability, right? And we want to know that can we find an extension of T, consistent extension of T associated with this method M, so that we have this property. We prove the consistency of phi, the relative consistency, because we assume T is consistent, the relative consistency of phi with this method if and only if this extension gives an actual proof. Okay, this is just a dream. So don't take it seriously. Or at least we want this, if we can show the consistency of phi with this method, then that extension proves. This is the opposite direction of the one, the direction here, the trivial direction, right? It's somehow opposite to this modulo the method. Okay. So, okay, you can just say that we can say that the method is finding that branch through the tree to find a complete extension. Okay, but we can put some restriction. We can expect that TM is consistent, it is easily expressible, it is functional, and even we can say that it is subject to Gödel's incompleteness theorem. So it cannot obtain in that way. Okay, so we can add more things if we want. In particular, it would be better if it is of this form, T, together with an axiom or a scheme of axioms. Okay. This is not always possible. without restricting things, because you have a method, maybe you use the same method and you prove the consistency of phi and the consistency of the negation of phi, and then you cannot have both of them, right? So you should make some limitations, some restrictions, and this is the beautiful part of this general idea. There are some examples, some sort of pseudo completions in set theory, like generic absoluteness, modal maximality principles introduced by Stavy and Van Anen and by Hankins, and inner models and forcing axiom. In all of them, there are restrictions over the complexity of the formulas, over the parameters we use, over the class of forcings we use, and etc. But we have still this dream that we want to enlarge it, and we want to get the best possible thing to prove theorems. So this has also the advantage. We don't need to repeat the arguments every time. So, okay, I mean, we can provide some philosophical justifications, but also mathematically, if we have such a thing, it gives us a clear, a transparent picture of the situation in set theory. And so we don't need to repeat an argument several times without knowing what is behind. And so this is the this presentation so far is sort of syntactical completion, but if we look at it semantically, it means that as it was pointed out by Anders, that if we have a universe, and if we, the maximality principle says that if we can make an object in a further universe, then it already exists there if the maximality principle holds, but it has always restrictions, and unfortunately they come to conflict. Okay, this is the general idea, and now you can forget about the beginning quotation, and we want to be a bit precise. So what is forcing? In this talk, we are interested in the possible pseudo-completions of ZFC given by forcing axioms. When we want to look at forcing axioms as sort of pseudo-completions of ZFC with respect to the method of forcing. Okay, so we need to know what forcing is, but it is not necessary to know all the details. Fortunately, when we want to work with forcing axioms, we can still work with it without knowing what a forcing is. The method of forcing was invented by Paul Cohen in 1963 to show that the continuum hypothesis is not provable in mathematics, or more precisely, ZFC cannot provide a proof for the continuum hypothesis. And this combined with an earlier result due to Gödel, it was shows that the continuum hypothesis is independent from ZFC. It's an actual, precise mathematical statement which turned to be independent. This was the first one somehow, yes, and then later other statements about groups or other mathematical structures also were proved to be independent. Just recall that the continuum hypothesis says the size of the real number is the first uncountable cardinal, or the second infinity, which is denoted by omega. So let's start with this, with the intuition that how forcing works without knowing what it is. Okay, it's a process as follows. We start with a finite fragment of ZFC, means that finitely many axioms, T, and then we pick a model for another finite fragment of ZFC, which extends the original one. It's just a technicality, it doesn't matter. Okay. And then we adjoin a generic object to M using an internal device, which is forcing. And we construct M of G, M square bracket G here. And it is shown that it is a model of the original one. Okay, this is just a general idea without knowing forcing. It's like if you are familiar with algebraic closure, algebraically closed fields, it's like you have a field and you add an object which is not there, and then you close it under operations, you get a new field or other kinds of closure. But here, this set theoretical structure M, over this structure, there is no operation. We cannot close it under something or saying that it's not easy to show that this set M of G is a model of T. I will talk about it later. And how does this process help us in independence? Okay, it works like this. If we have a statement S and we assume that FC is consistent, and we want to show that this statement, for example, continuum, the negation of continuum hypothesis or whatever, is consistent with CFC. So we know that if it is not the case, then there is a finite proof for the negation from ZFC, right? So this finite proof uses a finite fragment of ZFC. We are in the first order logic. And let's say this is T. So we enlarge this T to a set S so that we can perform forcing. And then we find the model M, and we adjoin this generic object to M, and we know that it's a model of T, and so the forcing is chosen so that the negation of the statement is true in this model. And this is a contradiction, right? Because, sorry, but here should be is not negation, okay? So because if there was a proof there, and that proof is still when interpreted in M of G should work, but it doesn't. It is not the case. Now, there are some questions. Why M exists? What is G? When G exists? How to construct M of G? And why everything works at all? And to answer this question, it takes, I mean, several hours to answer these questions. But we are here, we are interested in just in questions 2 and 3. Not the rest, because we are not going to do forcing, we are going to introduce forcing axioms. Okay, so here is a simulation. Many people are familiar with this. So we can think about the theory of fields. There are a bunch of axioms saying that what kind of rules we have about addition, multiplications, and so on, like a usual arithmetic in real numbers we do. And we can consider an equation, a polynomial equation like this, x squared minus 2 is 0. And ask if it has a solution, if the theory of fields can prove that there exists an x so that x squared minus 2 is 0. So theory of fields, we can ask the question that if the theory of fields proves that there is a solution for these polynomial equations. And we know that this is not the case. How we know that? Okay, we know the rational numbers Q with the usual addition, multiplication, and so on. It's a field. And there is no root for this polynomial equation. So in that model, the negation of this statement means that for any x squared minus 2 is non-zero, holds. But on the other hand, in the field of real numbers, this is true because we know that there is a root for this. Okay, now this just says that this statement is independent from the theory of fields. It's good. Okay, that's by magic we know that there is such a model. Unfortunately, in set theory, it doesn't work like this, but it is similar to the following situation. We can start with the field of rational numbers where there is no solution, there is no root for this polynomial equation, and add the root to this and close it under multiplication and addition and so on, and then you obtain a field where there is a root. Okay, that's good, but as I mentioned already, it doesn't work for models of set theory. So, you know, I mean, for example, what do you do if you're a student asks that, okay, suppose we don't know what the real numbers are. So I don't know the square root of 2. How you can extend Q to find an extension. How you want to extend Q so that you have a root, and or for example, obtaining this without closing under operations. So set theory, in set theory, M of G is constructed in similar to another construction of Q, this field Q round bracket square root of 2. That is, so let me, okay, let me illustrate this situation in set theory. Suppose you have other equations and you are asked to add a root for this polynomial to your equation, but so that you don't add roots to other equations. But maybe this is impossible, right? Because you destroy things. Maybe you add a square root of 2 and it produces a new number, and that number is the root of another polynomial. This happens in set theory. So you want to add something, okay, you add it, and it satisfies the things you want, but it destroys other axioms. It is like that. If you want just to get the idea, is that you look at the polynomial rings. The polynomial ring, the ring of polynomials, this is not a field. And suppose that you don't know what a ring is. It is something like a ring. Some elements have inverse, some don't have. So, but each of them has a degree of how to say. There could be elements that they are not, they don't have inverse, but they are different in the sense that when you take the quotient by maximal ideal, some of them turn to be invertible, some of them not. So you see that the truth there is fuzzy. So you can, the elements are either invertible or not, but they are different. Set theory is like that. You make a new word. It's not like set theory, it's something. It's called the universe of names, and then you take quotient by maximal filter, and it interprets things and turns things to be actual sets in some sense. In the polynomial ring, when you take the quotient, you by maximal ideal, you make it a field. I mean, there could be a beautiful correspondence between these two concepts, but still the models of set theory are very wide. So, okay, so let me point out that here I mentioned that to internalize this method, this G is an object coming from approximations. So we need to consider the set of approximations inside M, and then find this generic object outside and adjoin it to M. Okay, now let's find some intuition. Recall that a topological space is a pair where X is a set and tau is a subset of the power set of X containing X and empty set. And tau is closed under arbitrary union and under finite intersections, where the elements of tau are called open sets. They gauge the proximity between points, and this is a good notion for approximations. So we want to use this idea and to see how it relates to forcing. A set is called dense in the topological space if it intersects every open set. So that means that D is close to any given point. Like coronavirus is dense, it is everywhere. Okay. This is the intuition behind open set, but it is not always that any topological space follows our intuition. Okay, we will see. One of the main, one of the fundamental tools in topology is the Baire Category Theorem. It has many applications. It's very easy, but very fundamental. It says that if X is a locally compact Hausdorff space, we don't need to know why we assume these things, then every countable collection of open dense subset of X has non-empty intersection. In some sense, it says that such a space is not thin, it's somehow large in some sense. And this locally compactness and Hausdorffness, it is just like make things more intuitive, meaning that when you have an open set and you have a point inside, when you find another open set, you can think that this is a better approximation, but maybe it is not really. This locally compactness says that you can shrink your open sets around the point in a correct way, meaning that when you shrink it, when you find a smaller set in the sense of set theory, it is really a better approximation to that point. You get closer to that point. And Hausdorffness is something like you can, this device, this topology, this collection of open sets, when we have 2 points, and set theoretically or mathematically, whatever, we know that these points are different. The Hausdorffness says that this device can understand this. You can find 2 open sets that separates 2 different given points. So the topology can distinguish individual points. So this is very intuitive, right? Without that, things may not work. However, they are still interesting. Okay. So we have many applications of the Baire Category Theorem in mathematics, and in particular in mathematical analysis, but maybe this one is not something that people can find in a textbook. But actually, we can use the Baire Category Theorem to prove that the set of real numbers, the size of the real numbers, is uncountable. It is bigger than the size of the natural number. And we can prove that every 2 dense linearly ordered countable set without endpoints are isomorphic. This is, in fact, every such a linear ordered set is isomorphic to the rational numbers with the usual ordering. It is sort of compactness given to us by the Baire Category Theorem. And here by compactness, I don't mean the topological compactness. I mean in general, we have a property. And if we have an object and sufficiently many sub-objects satisfies that property, is enough for the property to be satisfied by the whole object. It's a very broad term, and it is not a precise mathematical definition. In particular, we don't know what sufficiently means. It could be anything. Okay, so we can also prove other results, which is not related directly to mathematical analysis. So we can make a statement and look at topological spaces and ask if we can have the Baire Category Theorem for these spaces. And so if we have, maybe we can prove more theorems, right? Or in general, we can even formulate a higher Baire Category theorems. So we say that the Baire Category Theorem for the topological space X and kappa holds if every kappa size collection of open dense subset of X has non-empty intersection. Let me also mention that this formulation of the Baire Category Theorem is just one formulation. There are other formulations like that. The intersection is dense, more than non-empty. Okay. But there is a better way to approximate objects in set theory, and that is partially ordered set. We call a partially ordered set, or a poset for short, is a pair P with a binary relation over that, so that it is reflexive, symmetric, and transitive, so completely intuitive. And when we say X is less than or equal to Y, then we mean X is stronger than Y. Intuitively, X is more informative than Y. Maybe, I mean, it is a bit notationally is counterintuitive, but remember that in topology, when we find a smaller neighborhoods, we find better approximations, right? So this is why direction is like that. When X is smaller, it is stronger. However, you can work with the opposite notation. It's a matter of taste. And we can define the same things. Say that a set is dense if for every P, in P, there is another point in D, in the dense set, which is below P, which is stronger. But here is a new notion. It's the notion of a filter in a partially ordered set. So a non-empty set is called a filter if it has the following two properties. One is that F is upward closed, meaning that if we have P in F and Q an arbitrary point, arbitrary element of P, and Q is bigger than P, then Q is also there in F. And if we have 2 points, PQ in the filter, there is another point in the filter which extends both of them. This is very crucial. It means that the objects in M are compatible. They don't have contradictory information. So if you have, for example, functions, that means that it is not the case one function says that the value of F at alpha is 0 and the other one says that the value is 1. So yeah, because you should be able to extend them, for example, by set extension. And this is sort of, okay, let's see this first, and then I explain what does it mean. Maybe the filter is not large. For example, if you have a point and you generate filter with that, it is just like that point. It's nothing. But you can guarantee that the filter is large by requiring the genericity. So we have a collection of dense subsets of P, and we say that G is degenerate if for every dense set G intersects D. So it is similar to the Baire Category Theorem, right? Okay, what does it say? You know, when we construct things inductively, we have the first stage, second stage, third stage, and so on. And then out of this construction, we can, for example, sometimes produce a large object by constructing small objects inductively. But this is sort of the, if you have a poset, you cannot even talk about levels. Okay, so you may extend things. Means you continue your construction and then you stop, you have to terminate the construction and so on. This filter is like magic. It comes there with a set of compatible information, and you can, in many, often you can put them together to construct a large object. So in some sense, this genericity is somehow an induction. It's an inductive process. And we have this theorem, Rajub-Sikorsky theorem, so which is like the Baire Category Theorem. It says that if we have a poset P and we have a countable collection of dense subsets of P, then we can find a large filter with respect to this countable collection. Okay, And we can, like as the generalization of the Baire category theorem, we can talk about higher Rajio-Vasikorski theorems by saying that if we have a cardinal kappa, if we have a poset, and then RST P kappa, means that for every kappa size family of dense subsets of P, there is a degenerate filter. That means that this filter is really large. Okay, this is not a surprise because for every compact Hasse surface space, ignore this technicality here, there is a poset associated with this topological space so that the Rajio-Vasikorski theorem at kappa holds for P of X. Then if Rajio-Vasikorski theorem holds, then the Baire category theorem, the higher version, holds for X. And for every poset, there is a compact Hasse surface space, the opposite direction, so that if the Baire category theorem holds for X of P, then the Rajio-Vasikorski theorem holds for P. So in some sense, the Rajio-Vasikorski theorem is sort of, we can say, generalization, or I don't know, equivalent formulation of the Baire category theorem. Okay, now what is a forcing? A forcing is just a partially ordered set. The name seems scary, but it is actually as a single object. It is a partially ordered set. It's a poset, but in mathematics, when we talk about posets, we usually mean a binary relation. So mostly we are interested in the first order properties of these, but in forcing we are not in general interested in the first order property of the poset. We are not interested in the ordering. We are interested in the compatibility and incompatibility. This is important in forcing. Okay, now let me give you a simplified picture of the method of forcing. Earlier I talked about the process of forcing, the method of forcing, using a model of a fragment of ZFC. The model should be small and so on. But let's forget about that and just believe this by your heart, that we have a transitive or the transitive of transitive universe of sets. It depends how you want to look at things. And you have a forcing, a partial order set. Then there is a generic filter, a filter which meets every dense subset of P. And usually this generic filter is not in V, otherwise it does nothing. And then we can construct V of G. It is again a model of CFC. This is the simplified version. So what is that? I want to add a function like adding a root to a polynomial. I want to add a witness for a statement, and I construct this in a generic extension. I don't have it, but I have approximations. And this generic filter put the approximations together in a coherent way so that out of this generic filter, I can produce a witness for the statement I want to be held in the generic extension. So this is the general idea why we use approximations. So there is an example. This is the first, I think, forcing. This is coin forcing. Okay, now what are partial information? They are functions from finite subsets of natural numbers into 0 and 1. It's like a finite subset of natural numbers. And we say that P is stronger than Q if P extends Q as a function. This is natural, right? And it is easily seen that if G is a filter, then the union of G is a possibly partial function, right? Because every two elements in this filter, they are compatible, meaning that the union is a function. You just take the union and it is easily seen that it is a function. But if we require genericity, V genericity means that meeting every dense set in V, then we can show that G is in fact the total function. And it is different from any other function, of course, any other function in V. So what does it mean? How to show that it is total and how to show that it is different? the point is that the elements of this poset C, which have a given natural number like n in their domain, is dense. So for any n natural number, the set of functions which have n in their domain is dense. So we have the genericity for all dense sets. So finally, there is something in this filter which has n in its domain. So this is a total function. And it is different because for any function in V, or for any subset of natural numbers, we can associate a dense set which consists of partial functions, so that for some element in its domain is different from that total function. Okay, and so again, by genericity, we make sure that this G, the function G, is different from anything. So this is the co-enforcing, and if you modify it a bit, you can show that in fact so in generic extension, in some sense, I add a real number which is different from any real number in V. You can do this, modify this, and show that you can add Aleph-10 many new reals. So, and then make the continuum or the size of the real numbers to be Aleph-10. Okay. So ZFC does not prove the Rajio-Vassikorski theorem for this poset and omega 1, right? Because if it proves this, then this total function is different from any list of omega 1 many real numbers. So then we prove in ZFC that the size of real number is bigger than Aleph-1. We prove the negation of the continuum hypothesis, which is not the case by Cohen. What about the negation? Does ZFC prove the negation of RST C omega 1? Okay, we will see the answer later. And on the other hand, we have posets that disproves the Rajio-Vassikorski theorem or the Baire Category Theorem when you just lift things from omega to omega 1 and you allow everything participate. So you cannot do that. You get contradiction. So you should be careful when you want to generalize the Baire Category Theorem or RST. A poset is called sigma closed if every descending sequence in P has a lower bound. So this is clear what it means. We can prove this higher version of Rajio-Vassikorski theorem just in ZFC, RST for sigma closed forcing, but meeting Aleph-1 many dense sets. And use it to show that 2 to the Aleph-1 is bigger than Aleph-1, the same as the real numbers. So let's see a summary. So far, we saw that mathematics is incomplete by Gödel's theorem. There are questions which cannot be answered based on the accepted formalism, which is ZFC. Forcing is a powerful method to show independence. And we are searching for consistent extensions of ZFC, which are pseudo-complete with respect to the method of forcing. Some forms of the Baire Category Theorem are also relevant to general questions in mathematics. The Rajio-Vassikorski property of poset is equivalent to the Baire Category property of some spaces, and they potentially imply compactness results, but it's not yet very visible. And some generalizations of the usual Rajio-Vassikorski theorem for various forcings and cardinals may be admissible candidates to pseudo-completion of ZFC. And here is the definition of forcing axioms. A forcing axiom is in this form, F(A)K kappa, where K is a class of posets or forcings, and kappa is an infinity, is a cardinal. And it states that whenever you pick a poset from this class, it should be, sorry for misprint, P is in K, and every sequence of dense subset of P of length kappa, there is a degenerate filter. Okay, this is This is exactly Raju-Sikorsky theorem for any P in K and kappa. So what does it say? It says that if you can construct a set by meeting at most kappa many dense sets, then such a set exists in that universe. This is not entirely true, but roughly speaking, it is. This is this pseudo completion, but there is a restriction. I cannot say that if something is forcible, then it holds. Okay, so I have a restriction and I pay a price for that. And is that if the object is constructed uses only at most kappa many dense sets, then I have that set. Not exactly that set, but maybe a set with that property. Okay, so we should be careful about this. But the idea is like this. This is like semantic version of the completion, meaning that you end up with a model which is sort of saturated in this, not in the sense of model theory, in the sense that it is enlarged as much as possible. Okay, so the good thing is that in many cases we want to construct, for example, an object of size Aleph1, the first uncountable cardinal. Then sometimes we need to meet only Aleph1 many dense sets. Okay, even we have full genericity, but we need only Aleph1 many. And this says that okay, you don't need to repeat things, and moreover, it gives a good framework to show the simultaneous consistency of several statements. Okay. There is an important notion, and now it gets a bit technical, but sorry for that. A subset of a poset A is called an antichain if for any two different points in this set, they are incompatible, meaning that there is no extension in P of them. So they have contradictory information. So this is somehow it is hard to say, but so the large antichains can be difficult to handle. So this is why I said a large amount of contradictory data may lead to destruction, but this is something that we should see in applications. And the fourth thing has the countable chain condition, CCC. It should be countable anti-chain, but I don't, this is some historical fact. If and only if every anti-chain in P is at most countable. So we don't have large anti-chains at all. And these are good candidates because the corresponding version in topological spaces is called CCC topological spaces. Topological spaces with the countable chain condition are those spaces that any collection of pairwise disjoint open set is at most countable. It's like separable spaces. It's very close to that notion, right? So the first forcing axiom beyond those trivial things which follow from ZFC is called Martin's axiom. It was discovered by Martin and Salovey, I think. Of course, I don't know, I have to mention Tenenbaum because, I mean, the results were very close. The first forcing axiom is that is about this class of posets, CCC, the class of CCC posets. And Martin and Salovey in 1970 showed that MA is consistent with all possible values of the size of the real numbers. Okay, I mean, MA, which states that MA kappa holds, and MA kappa means meeting kappa many dense sets by CCC forcings. Okay. Note that MA omega just follows from Raju-Sikorsky theorem, and MA the size of the real numbers, or 2 to the Aleph 0, is false by the Cohen forcing, because if it was true, then we can produce another real number which is not in the list. So This is a contradiction. And MA kappa, for the same reason, implies that kappa is less than the size of the real number. And MA, the Martin's axiom, says that MA kappa holds for any kappa less than the size of the real numbers. So of course, if CH holds, then MA holds, but then MA is just MA omega. This is nothing special here. So the question is when we can have MA omega 1, MA omega 2, and so on. And it, in fact, MA is consistent. It was proved by Martin and Solovey. It's consistent with any value of the size of the real number. It has many consequences in mathematics, in set theory, everything. It's a first forcing axiom, and there are, I mean, thousands of results which follow from MA, but MA is not strong enough in some sense because it, for example, it cannot settle the size of the real numbers. It is compatible with some counterintuitive things, but I think Martin's axiom is very powerful. It's very strong because it is independent from the size of the real numbers. So we will see why it is powerful. Before that, let's see how people obtain forcing axioms. If you like to obtain one forcing axiom, you should do the following. Okay, we know that when we perform a forcing, it adds a single object. Of course, it may add many objects, but that generic object, generic filter, I mean, over the universe. Then we can iterate this process as long as we want. And this process can be internalized, and of course, and in fact, shown to be equivalent to a single forcing, which is called iterated forcing. So we have this process, it's an iteration of the forcings, and then we make a forcing inside the universe, which is this iteration. Oh, okay. I think I don't have enough time. I thought I have still 10 minutes or so. Okay, so these forcing axioms later people generalize.
You don't have to finish in 1 minute, but okay, just in a few minutes, right?
Okay, thank you. So the problem is about this iteration. This iteration may not work. So all the problem is that to find iteration theorems, which says that if we iterate this class of posets, then we preserve these cardinals, that cardinal, and so on. So let me just finish it slowly. And the generalizations, I mean, the natural generalization of Martin's axiom at Aleph1 does not work for example, Aleph2CC, the analogous of CCC. We need to add some extra conditions like closure property, and even that one doesn't work. I mean, the forcing axioms, so the question is that we want to find a strong forcing axiom meeting Aleph2 many dense sets. The forcing axioms for meeting Aleph2 denses, of which we are aware, are weak. They cannot prove many things. They are compatible with things we don't want. So this is a very big problem, big project in set theory, to find higher forcing axiom, a strong higher forcing axiom like PFA, the proper forcing axiom, which was discovered by proper forcings were introduced by Shelah, and PFA was introduced by Baumgartner, and Baumgartner himself showed that it is consistent. For example, it was shown that PFA implies the size of the real number is Aleph2. It was shown by Velichkovich. This is highly non-trivial, and it is the opposite direction of MA. And there is still generalizations of this, but I am not going to talk about these things. But it was shown that the straightforward generalizations of PFA does not work. And finally, In 2014, Rahman introduced a new method, which it's a bit technical, but it shows that probably we can find a higher forcing axiom meeting Aleph too many dense sets, strong higher PFA. And but this is a long way to go, and we leave the following question to the future: if Rahman's method is a paradigm shift because it's a new phenomenon in the theory of iterations. And so the conclusion is that we don't know anything about omega 2 or omega 3, or at least I don't know. And here is the story. I give you 1 minute or 2. You can read yourself. Thank you.
Thank you very much, Rahman. Your exposition, your talk was very interesting. Especially, I see here some of my students who are taking a class in set theory reinforcing, and I'm sure that this is giving them a new perspective. Thank you.
Thank you.
Do we have any questions from the public? So the text, perhaps I should read this text to everybody.
Oh yeah. Do you see?
Yes, can you please, what happened now? Truth is vulnerable, applicable to Thai case is the story of that fox which people saw running away in violent trepidation. Someone said to him, "What calamity has happened to cause thee so much alarm?" He replied, "I have heard they are going to impress to make fun of the camel." They rejoined, "Oh, Shatterbrain, what connection has a camel with thee? And what resemblance has truth with?" He answered, "Peace. For if the envious should, to serve their own ends, say, this is a camel, and I should be taken, who would take care about my release so as to inquire into my condition? And before the antidote brought from Iraq, the person who is bitten by the snake may be dead." Sadi Shirazi, Goldstone, translated by Edward Istwick. So truth is vulnerable. I guess you can be taken for a camel even if you are not. Thank you. Very nice story. I like it very much.
Thank you.
Did you have a question about this, Boban? You were going to do what? Yeah, did we? I think we uploaded, but we'll see if we have questions from the online participants.
I don't see the chats. If there is a question, let me see. No, there is no question.
No, well, you explained everything to us. So thank you very much, Rahman.
Thank you for
giving us this walk through the forcing axioms, and keep us updated with the news, which I'm sure you will be contributing to the news in this subject in your own work.
Thank you very much.
Bye. And for us here now, we have a break until 3 o'clock. And yeah, so see you there.
Back at 3 o'clock.
Yeah. Oui, en fait, on peut maintenant parler en français. Voilà, on revient à 15 heures.
À 3 heures. Je viendrai à 3h moins le quart. Je ne peux pas manger avec vous, je m'en explique. Je viens à 3h moins le quart pour qu'on installe l'après-midi peut-être.
D'accord, mais je ne sais pas s'ils vont nous laisser entrer là. Est-ce que tu as dit qu'on rentre à 15 heures? D'accord. Tu dis à la dame à l'entrée qu'on peut revenir.
Bien sûr, j'ai la clé. Ceux qui restent, j'ai la clé, donc vous pouvez laisser vos affaires.
Ouais. Et moi, je vais peut-être aller chercher le câble. Oui. Donc, Mathias.
Marina, ouais, tu peux arrêter parce que je suis à distance là, mais j'ai bougé. Est-ce que tu peux, j'arrive pas à arrêter à distance. Ah si, c'est bon, voilà.
Quitter la réunion.